So this is mostly just the introduction to deep learning. We're going to talk about deep learning or the application of deep learning in other areas, in future weeks as well, like in diffusion models, in large language models, so on and so forth. So these two lectures are mostly just setting up the basics of deep learning, especially in the context of supervised learning. We are going to introduce just a general framework for supervised learning for nonlinear models, which is pretty much the same as what you have seen in the lectures by Chris again about linear models. You just extend it in a pretty simple way to nonlinear models. Then we're going to define neural networks, which is the most popular nonlinear models, if it's not the only nonlinear models people are using. Of course, there are many variants of neural networks. We are going to define some of them and some of the basics. And in the Wednesday's lecture, we're going to talk about backpropagation, which is about how do you compute the gradient of the loss function with respect to these models, so that you can train these models by computing the gradient and update based on the gradients. And I'm going to use the whiteboard, and the reason mostly just because I found that when I use the slides, there's only one slide there, right? So there's not enough memory there. So once I switch to the next slide, sometimes people don't remember the previous slide. And also this is a regulating effect for me to slow down a little bit, because after teaching this for so many years, I tend to speak fast and go very fast. And this, at least, you see some, you see 6 bars as memory, so you can check them if you forget, and I can check them if I forget about something. And it's still not that slow in some sense. And feel free to ask me questions, because as I said, once I teach this kind of lectures so many times, I tend to move a little bit faster than I should do. And also, but we did update the lectures over time. So some of these new materials are new, and we drop some of the other materials that are a little bit out of date. Anyway, but generally still, this lecture is still just a very basic stuff for today, So I guess, I think you have, Chris has talked about a linear model, which is kind of like you have a model which is parameterized by theta, and the input is x. Let's just recall the notation so that we're on the same page about notation. I think Chris is using almost exactly the same notation. It cannot be exactly the same because sometimes it's non-linear model, right? So, but for linear model, recall that, if you have a linear model, then the model is kind of like this, right? You have h theta x, which is equal to theta 1 x1 plus theta 2 x2 up to theta d xd, where x is the input, which is a d-dimensional vector, and theta is the parameters, which are also a d-dimensional vector. And once you have nonlinear models, what does that mean? Generally nonlinear just means that as long as this form is nonlinear, then it's nonlinear. And here we are mostly talking about nonlinear in the parameters, because if it's nonlinear in the data, it's not nonlinear enough in some sense, right? Suppose you have something like theta 1 x1 square plus theta 2 x2 square, so on and so forth, theta d xd square. I think we didn't talk about this kind of models, because we skipped them in some sense in the new version. But this is not sufficiently nonlinear to be interesting, because you can just define new data, which is the square of the old data. So suppose you say, I'm going to replace this by Z1 and replace this by Z2, and then it still becomes a linear model. And anyway, you are not learning you are not trying to find out what are the, you are trying to learn the theta i's, right? You're going to figure out the parameters of theta I. You don't really have to figure out, there's no learning on zi's, right? So whether z is zi or xi square, it doesn't really matter, right? So that's why this is not exactly what we're talking about, even though some people will say this is still a nonlinear model, but this is not exactly what we are talking about. We are talking about cases like you have theta 1 square, for example, x1, plus theta 2 maybe. I'm just giving an example, something like this, right? Whatever nonlinear model you can write, as long as it's nonlinear, is called nonlinear model. Okay, so of course, the real model we are talking about is not that like this. This is just one example. So the model we are going to talk about is neural networks, which is more structured and more specialized way. Anyway, but before talking about neural networks, let's talk about how do you learn nonlinear models, and what's the kind of the framework. This is in some sense mostly just recalling what Chris was talking about, with a little bit twist about, the model. So basically the model can be a general function as opposed to a linear function. So let's just quickly recall some of this. So let's say you have a data set. I think Chris probably mentions the concept of data set, which is a family of data points with pairs of inputs and outputs. So here, let's talk about supervised learning, by the way. In other cases, we have data sets of different format. But here, if you have a supervised learning data set, you have a sequence of input and output pairs. And let's say we have n of this. Let's say we assume xi is in D. And just recall that in this lecture, in this whole course, we are trying to use this notation where the superscript is for the indices of the examples and the subscript is for the dimensions, the coordinates, right? So when I write x sub I, this is the first coordinate of the vector xi, and we have superscript is indexing one particular example. Go ahead.
Where you explain the nonlinear models, you're saying that is that nonlinear just x or is it also nonlinear data? And what is the difference between the square root expression and the one variable?
Yeah, that's great. So if you are only nonlinear in x but not nonlinear in theta, then it means that you can replace the x by something else, right? You can replace xi, for example, in this example, you can replace x1 squared by z1, and then you just say z is my inputs now. And then I have a linear model in both z and theta. So fundamentally, it's the same as linear model from a learning perspective. But here, you cannot do this, right? There's no way you can easily transform it into a linear model. Actually, there's no way, just fundamentally. So that's why it becomes, it requires different kind of slightly different kind of techniques, right? So some of the linear model techniques cannot work anymore.
And that's just one example of a potential nonlinear.
Yeah. You can write, This is just the one, you can even add more things, you can take more square roots, whatever. You can take squares, You'll see some real examples. Yeah.
You talk consider work if you just added another data and then x1, but so not like an x1 squared with that circumvent the problem.
In which cases? In this case?
Yeah, like if we just had no x squared terms.
Okay. Sorry.
So you would add on data d plus 1 x1 instead of x1 squared.
I didn't get what you mean. So you add on something here?
Yeah, just x1 instead of x1 squared.
So you add one of these two?
Yeah.
But then you change the model, right? Suppose my model is really suppose my model assumption is just literally this. What my argument was that you can replace x1 squared by z1 so that you maintain the model's functionality, but you can reapply the same techniques that is useful for linear models. Okay, sounds good. So anyway, okay, so how do we, so now let's just assume we have a general, okay, so let's talk about the framework. So, and you have let's say we have a regression problem. I guess, Chris' lecture talked about regression versus classification. And for regression problem, let's say, one of the distinction between regression and classification is that we have a regression problem, the yi, the labels are in real number, right? These are real numbers. And then your model, let's say, is the h parameterized by theta, which is a function that maps the input, which is the rd, to a real number r, right? And you can have a cost function, or maybe loss function. I think these days people use the word loss function more often. In the lecture notes, we still use cost function, but most researchers understand what you are talking about. So this is the most likely. Of course, there are also many different type of mean square error functions or loss functions you can define. By the way, error and loss and cost is the same. Let's just use loss for all the cases. And the loss function could be something like this. With J, for the ith example, the loss function is a function of the parameter because the data is not something you optimize for, right? It's not not a variable, it's given. So loss function for the J's example is yi minus h theta xi. You apply the data, you apply the model to the data, you get some prediction, and you compare that with the real label, and you take the square, right? Something like this. And then you can also have the average loss, which is something like 1 over n times the sum of all the losses. So, and then you try to minimize this function over the parameter theta. So that's for regression. And let me give another example. I think you are, this is mostly just repeating some of the stuff we have discussed. The only thing is here is just that this is a nonlinear model as opposed to a linear model, right? So in quiz lecture, I think this is just theta 1 x1 plus theta 2 x2, so on and so forth. And I guess for multi-class classification, we can also talk about single class classification, but which is actually in the lecture notes. I think I just thought, given the interest of time, let's just only talk about multi-class classification. Basically, you just have to define the loss function the same way as we have done for linear models, except that you replace the models by nonlinear functions. By the way, I think in most cases you don't have to think about the superscript I, because this is just indexing examples, right? So if you say I only have one example x and 1 and x and y, then everything without a superscript still works. Maybe I should just write in that notation to simplify it a little bit. So let's say you have, so in this case, the y, I can write y superscript I for the ith label, or I can just use y to indicate one label. Let's say, suppose you have one label. In multi-class classification, you have, it's a discrete choice of labels, right? 1 to k. And here, I guess, you can say you have a model, let's use h bar, which is mapping the input x. So the x is still in RD. Think of this as an image. Think of this as some kind of labels for the image. And then which is mapping the input to k numbers. And these k numbers are often called logits. This is the same logits in the linear case. So, and then you say with this logits, the predicted probability of each class, for this example x, for each class, let's say class J, is this kind of exponential form, right? You look at the J's, this is the J's output, right? Index J means this is the J's output of this k-dimensional vector. And then divided by the sum of the exponential of all this is the so-called softmax. So this is the so-called softmax. So this is the so-called softmax function of this h. And then, so basically you say, so basically your model is like this, right? So this is your model. So P of y is equal to j given x is this. This is my parametric model for the prediction parametrics by theta. And then I need to compute the log likelihood. So I'm going to use negative log likelihood, which is also what we have discussed before. By the way, here, this is also a log likelihood model if you assume there's some Gaussian probability distribution. I didn't really go through that calculation. So if you think of that your probabilistic model is something you add a Gaussian to the h theta, and then you compute the log likelihood under that Gaussian, then it's the same mean squared error. Here, I'm just going through more details. So, I define my probability distribution. I compute log likelihood on the data. So this is the minus log P of y given x, and my parameterized model. Then this is a minus log of this thing. So, sorry. I think one subtlety here is that so this model specifies what's the probability for every choice of j. But now I have a particular choice of j, which is equals to my label y. So that's why I'm going to plug in my y. So this is exponential h theta bar x. This is for the particular label I'm given. The width index, the width coordinate of that logit vector divided by the denominator is the same, just the sum of the exponentials. Oh, I think I have some typo here. And this is just called the entropy loss. I think if you look at the multi-class classification case, this is the so-called cross entropy loss. You can have many different form of it, but this is the cross entropy loss, where you can just write this H theta bar X, Y. So this is the logis, this is the label, and you can plug in the cross entropy loss. If you use PyTorch to implement it, I think you can find the modulo, which is just called cross entropy loss, and you give it to the inputs, and you can compute the loss. But of course, the underlying math is this. Okay, this all sounds somewhat familiar to some degree. Okay, good. Any questions?
Can you explain why it's called cross entropy loss? Like, is there a reason that entropy?
Is cross entropy? Is there? So what's the second part of the question?
Like where can we see entropy within the equation?
Yeah, I think this is the cross entropy between the probability distribution defined by H theta X. Okay, so I think here's the thing. So the question is why this is called cross entropy loss. I think if you, how do I write it in some sense? Like, I think if you have let's say this distribution, let's call it, maybe P theta. Okay. So, and, I think this cross entropy loss is actually equals to the cross entropy between the true, I guess you have to take, if you take the expectation of this L cross entropy loss of this H bar and Y, and the expectation over Y from the true distribution, from the true label distribution, whatever you call it. And then this is equals to a cross entropy between this distribution P theta and the true distribution P star, which is something like I guess the cross entropy is just it's actually the probability of one distribution times the log of the probability of the other distribution. Yeah, I think the derivation is probably a little long, especially if you read in this language, it's a bit cumbersome, but this is a fundamental. I think actually probably I have it in the lecture notes. I forgot exactly. Yeah. Any other questions?
Why would be a one-hot?
Why? What is a one-hot vector?
Just like,
see, in my case, in my notation, Y is just a discrete variable. So that's why you can see I have H theta bar theta X indexed by Y. Y is like 2 or 3 or 4 or K. So, but if you can also write Y as a one-hot vector, which is the same thing, right? So like, then your math needs to be a little bit different, right? Then this is going to be the inner product between this vector times the one-hot vector. Yeah. But here I'm just using Y as really a discrete choice between 1 to K.
The log dimension with like the Gaussian distribution.
So, can you repeat the question? Sorry.
Yeah, you mentioned like with regression, if something is Gaussian distributed, it has some sort of, like it simplifies to. Okay,
so the question is why for the regression case, it also is not log likelihood, right? So I think let me try to see why I can do it on the fly. I think it should be easy. So I think the modeling, so if you make the modeling assumption that if you assume, suppose you assume that your modeling assumption is that Y is generated from, say, H theta bar theta X plus some Gaussian noise, but epsilon is from N0, maybe sigma square, something like this. Then the likelihood of Y given X is, I think 1 over, I guess this is challenging my memory of this, something like this, exponential Y minus H theta X square over 2 sigma square, I guess, something like this. And then you take the negative log likelihood. So then this is a log of P Y given X is equals to, there's some constant, you take the log, you get a constant, which doesn't really matter. And you got the log of this, which is 1 over 2 sigma square Y minus H theta X square. So then it's kind of like this, right? The scaling doesn't really matter because this it doesn't change the optimization function fundamentally. Sounds good. Any other questions? Okay, cool. So, and in this case, here I only have like one example, right? Eventually you're going to average over many examples, right? So, I guess maybe just, let me write here. So if you continue here, so eventually your loss, your real loss is something like the final loss is the average over all the examples. You take the cross entropy loss of each of the examples xi and yi. So, and each of these functions is a function of theta. So basically your total loss is also a function of theta. And now the next task is to optimize to find theta that makes the loss smaller, right? The same, I think we also introduced a little bit about like gradient descent, like a Newton method, right? So these are all ways to optimize things. So here you cannot use Newton method because the function is not convex. So that's why Newton's method is not guaranteed to work. Actually, no methods can guarantee to work for all non-convex functions, but stochastic gradient descent seems to be a good idea. So just to quickly recall, you can use an optimizer. So optimization, I think one of the options is you take gradient descent. So let's say, suppose you have a loss function. Let's just summarize all the cases as this. Let's just be a little abstract. So let's say each of the examples have have the loss ji of theta, and you have an average of these loss functions. Gradient descent means that you just say, I'm gonna ignore the structure here. I just treat this as a single loss function. I take the update theta is updated to, I think we use this notation to denote update, something like eta times gradient of j of theta. So this is gradient descent. And how do you compute this gradient? You compute the gradient of each of the loss, you compute the gradient of each of the loss with respect to parameters and you add them up. Right, so that's gradient descent. And for stochastic gradient descent, so what you do is you say your first sample, say B, let's see. So you sample, I guess there are, maybe let's say the most vanilla version of it is you sample one item, you sample J from 1 to n uniformly. And then you run this, so of course there's a for loop, and you sample, and then you say theta is updated to theta minus eta nabla. The cost of the example J, the cost of loss of example J theta. And the kind of the justification here is that if you think about what this is, so the difference here is that here you compute the gradient of the average loss, and here you only compute the gradient of one single example, the loss on one single example. And the justification here is that you say, even though this is one example, it's not actually the loss of the whole gradient, but actually if you look at the expectation of the gradient, the per example gradient, and your randomness come from J, right, which is sampled from uniformly from 1 to n. This is equals to the gradient of the average gradient, the gradient of the loss function. So in some sense, this quantity is an approximation of this quantity. And the approximation is in the sense that this quantity in average is equal to this. It's just that sometimes it's biased towards it's never let's say suppose this quantity is like in this direction and this quantity is just it can be any directions, but if you average out all the possibilities, you get the original direction you want to go. So in some sense, you have like a much larger noise, right? So like if you do gradient descent, it's kind of like, I guess maybe let me use two different colors. So suppose you use gradient descent, this is the gradient of the average loss. And if you use stochastic gradient descent, it's stochastic, you may go here, you may go here, right? You may go here, sometimes you may even go in the reverse direction, but in average, all of these blue ones will average out in the same direction as the black one. And then if you have a trajectory, right? So suppose the black one goes like this. The blue one, because it's stochastic, you have noise, right? So it will go look like this, right? Maybe something like this. Maybe like but in average, it's kind of roughly tracking the gradient descent. Of course, how much this tracks, how much these two things tracks over time is a very complex kind of like a matter. Like it depends on how large the step size is, how, kind of like it depends on many kind of like subtle things, but conceptually, you should expect that the blue one, some would track the black one. The blue one in average is exactly equal to the black one in one step. But the error sometimes can be amplified, sometimes the error can be shrinked. So it depends on the situation. Ideally, you want them to track to some degree.
Generally, you want to use stochastic gradient descent on a non-convex function.
I think you can use gradient descent as well. So okay, but I think you're getting at the question. This is great. I think it sounds like the question is really about why you use stochastic gradient descent. In what cases you want to use stochastic gradient? That's a great question. So why you even consider stochastic gradient descent? The reason is that computing this gradient is very costly each time because you have so many examples. N could be, in 2015, it's kind of 1 million examples. In 2026 now, I think it's kind of like, like 1 trillion tokens, right? There's no chance you can compute all the gradients. Even computing one gradient is very costly, let alone computing all the gradients. So that's why you have to find an efficient way. So that's why you want to have a sampler which is less costly. And maybe just one. So and also another reason you can do this is that computing the full gradient sometimes is actually wasteful. Because maybe it's the case that all of these individual gradients they are correlated. They are highly correlated. Right? So there's no reason to compute each of them to understand which direction to go. Right? So you just only need a sub. It's kind of like every example tells you to go that way. Why you have to compute all of them? Right? You just need a subset of them. And another thing is that even this is not entirely true. In many cases, you don't really have to be very precise in this dynamics. It's kind of like even you have some mistakes, it will be corrected later. So maybe another way to think about it is that for some cases, for example, if you have a convex function, right? So in some sense, one way to do it is that you do this, right? But sometimes if you kind of overshoot, or maybe you go in the wrong direction, still eventually you're going to go down. How do I say this? Basically, even you have some perturbations, and this is not exactly the right example, but even you have some perturbations in your dynamics, then over time, because every time you have to share a target, eventually those kind of perturbations got kind of washed out, by the shared force in some sense.
So I just wanted to ask, on a non-convex function, you might get stuck having local minimums, and I believe that this is where you should use stochastic gradient descent. Are we still able to use gradient descent, or would it not be?
Yeah, I think that's a great question. So one of the theory for why stochastic descent is good is that it can work better on non-convex functions. And maybe let me first expand what you said, but actually it's not entirely right. So I think so basically, suppose you have a non-convex function in 1D, right? Let's say, right? So like this. So if you start here, you keep going down. This gradient descent just means you go downhill in some sense. So you go to the directions which is going downhill sometimes it's called steepest descent. It's basically you're finding the direction which is going downhill the fastest in some sense, right? So you just go here and you get stuck here because you can never leave this place, right? Here the gradient is 0, right? The curvature is 0. I think what you are trying to say is that if you do stochastic gradient descent, because there's some noise, maybe even though you want to go this way, maybe the first step, because of the noise, you go the other way and you jump to another local minimum. I think this is plausible, but generally speaking, of course, the theory here is kind of very limited, but I think the community don't believe that this is the case. This is why stochastic gradient descent is helping. I don't think people believe that stochastic gradient descent can help you to jump out of a local minimum. However, on the other hand, we don't even believe that there are many bad local minimum. So in 1D, it's actually very easy to have local minimum, but in high dimensional cases, it's not that trivial to have that many local minimum. So I think at least one, actually I was involved in developing some of the theory. Of course, nobody really knows exactly whether they are right, but the common, let's say hypothesis or hypothesized consensus in some sense is that, there are very limited number of bad local minimums in this high dimensional function you're optimizing. Maybe there's even no bad local minimum. All the local minimum are actually global minimum. It's kind of like if you think about it, you are skiing in a mountain. I think if you just randomly try to go down skiing down hills in 2D, right? You're probably going to go back to one of the parking lots, which is one of the global minimum, right? So but in 2D, I think it's a bit easier to have a local minimum. You probably go backcountry and you got stuck somewhere. That's possible, but you always find some river going down. You always find some valley going down eventually, I think, I'm just going to give an analogy. It's not exactly sure in 2D, but in high dimensional, it's more likely to always find a way to go downhill in some sense.
Could you give some allusion as to the mathematics that actually shows why, which I would find to be counterintuitive, you don't see that many local minimum in higher dimensional spaces? I just find that kind of surprising.
Yeah, I don't think there's a very simple way to say it. I think it's not universally true, right? So in some sense, it's just, I think maybe if I can only use one or two sentences, I think it's kind of like, just in high dimension, there's always some ways to, the local minimum means your hashing at that point is just in all directions positive semi-definite. That's a very hard thing to satisfy. So you find a stationary point where the gradient is 0, and you create a hashing. The hashing is kind of like, always have some direction which is negative. And I think, I was thinking about how to formalize this, so for example, if you think about it, the gradient 0 is already a pretty strong constraint, right? Suppose you have a d-dimensional function and you add d constraints that each of the dimension of the gradient is 0. That's already restrict yourself a lot. And if you add another thing, which is the hashing is positive semi-definite, I think that just makes the number of points much smaller. Yeah, and in some cases you can compute. In one of my papers, I think we try to compute the number of local minimums by using this. I think in differential geometry there's something called Cass-Rice formula, and actually not only my papers but many other people's papers. So in certain cases you can compute and you can count, and you found out that all the local minima are actually just those number of local minima is the same as number of global minimum, but generally it's very hard to count. Yeah. Any other questions? Okay, sounds great. So going back to here, so that's the algorithm people do. Of course, practically speaking, you don't also just only sample one example each time, because sampling one example, using all the examples is too inefficient because you have to compute all the gradients. Doing one example, the downside is that it's too noisy, right? So sometimes you want to have like a trade-off, right? So you want to have a few examples, and so that you can be a little bit less noisy. And another thing is that, which probably we won't go in detail here, but another thing is that, when you have, one example, your GPU utilization is too low. It's not always the case, but in some cases, using too few of examples make your GPU utilization too low. For example, if you have like 10,000 GPUs and you just only compute one example of one gradient each time, then most of the GPUs are actually idle. So that's why you need a so-called batch gradient descent. Oh, sorry. I think it's also still called stochastic gradient descent with some kind of like small batches. I think SGD just means like both the version with batch size 1 or a little bit bigger batch. So when you have a bigger batch, you can imagine what it is. Basically, you just say, I'm gonna, with batches, I guess let's call it SGD. So I think you just change the algorithm to be you sample, say B examples from 1 to n, and then you say theta is equal to theta minus eta gradient. Okay, Sounds good. So, and, okay, so this is just a general introduction to the framework for the supervised learning. And actually in some of the unsupervised learning, it's the same thing. You define a loss function for each example, and you average them. The only question is when you have unsupervised learning later, that we'll cover, you don't have the y's. So, but still the kind of the framework is the same. You define the loss functions, but the loss functions then involve y, and then you have average loss functions, and you run the optimizers. You can choose different type of optimizers. And then pretty much there are two questions. So, we're going to address. So the two remaining questions, question one is that what is this function h theta, right? So we haven't, right? So this whole framework, works for every function h theta and, or h theta bar. I think I use bar just because, it's a little bit different, without bar, it's just, I just want to distinguish it from the regression case, but they mean the same thing. And question one is how do we define h theta? And question two is how do we compute the gradient J on each of the example. And once you know how to compute the gradient for each of the example, you can compute the gradient for all the examples or batch the examples, by averaging the gradient for every examples. So, and that's called, so this is called backpropagation. The algorithm for this is called backpropagation or auto differentiation, which is the topic of next lecture. And in the rest of this lecture, I'm going to define a bunch of h theta that people are using. Mostly for like more classical cases, like vision cases, like supervised learning, of course, for language case, you're going to have even more complicated, nonlinear functions like transformers. Okay. So that's the plan. I'm going to start with, the very basics, like neural networks. So we are still using these kind of housing examples. I know that this example is probably too old, like it's 20 years old. So let's say suppose you have like to motivate the introduction of like nonlinear models. Suppose you have like size and like this is the price, right? That's housing price prediction. So if you look at the real data, most likely it's something like this. Maybe I don't know exactly what it will look like, but at the beginning it doesn't increase that much as the size goes up, and then eventually it becomes linear. Let's say this is the case we will see in the data, right? So, if you use a linear model, you're going to fit something here, then you're going to not be accurate enough. So that's why, you probably have to have a nonlinear model, which is something like this. So you want your model to be able to output a curve like this. Of course, you don't really know which line is this. It could be like a priori, without seeing the data, you can have multiple kind of like curves like this, but at least you should allow the model to generate a curve like this, as opposed to only generating a linear function. So, and what this function is, right? So this function, is actually of this form. So this blue function is actually of the form, it's a max of, say, wx plus b, which is a linear function, and 0. I guess, especially if you, suppose this is 0, then you just, maybe let's say this is max wxp and this 0 plus c. So max of wx plus b is kind of like a function like this. And then if you, this one is like this. And then if you plus c, you can shift it above or below a little bit. So basically you just cut off everything that is below 0, which makes sense because, for housing price, it cannot be negative, it has to be positive. Yeah, okay. So, so this introduces a primitive that is used very often in deep learning these days, which is this function, which is max of t and 0. So I think in mathematics, people call it this, like people write this, something like this, but for us, we just call this value. I think this is the standard in machine learning. So this function is called rectified linear units, which is literally just this function where you have linear functions on the positive plane and then 0 on the other side. So 0 and then linear. and linear with slope 1. So this is a very important primitive. And then you can write this function as, this function can be written as ReLU of t maybe plus c, something like this. Oh, sorry, ReLU of, let's say this one will be written as ReLU of wx plus b plus c. So basically you introduce, so you see if you don't have the ReLU, then it's basically a linear function. But if you have the ReLU, then you somehow change the shape a little bit. And also this ReLU is often called activation function. I think the reason for the word activation is because there's some kind of like connections to biological networks. I think in biology, like in our brain, the neurons kind of like how the neurons are fired up is a nonlinear function of the stimulus it receives from other neurons. So, and it's not exactly this, but it's something like this, right? So like when it's passing some threshold, the neurons got fired up and below that threshold, the neurons just doesn't do anything. So that's why it's called activation, right? If it's fired up. So, but I think in biology, I'm not an expert there, but, based on my, knowledge of it, like the threshold, the function is never exactly like this. Sometimes it's like it's sigmoid. I think that's why sigmoid was used at the very beginning of deep learning. But then later on, people realized that this is actually, this ReLU is actually a better idea, for neural networks for various computational reasons, which we'll probably discuss in a bit. Anyway, so for now, I think that's kind of like just to remember this concept. So actually, we have already defined a one-dimensional neural network. So basically, this is a neural network with one-dimensional input and a few parameters. So that's already a neural network. So then the rest of for like 10-15 minutes, we are just going to generalize this to multiple higher dimensions, and you apply this multiple times, and that will make a more complex networks. And then we're going to even build more on top of that. So, okay. So next, what do we do? So this is only one-dimensional input, right? And so now let's try to do a higher dimensional case, right? Say, suppose you have a data with dimension d. And then how do you kind of like imitate this and make it nonlinear? So the way to do it is that you say, I have x in d, and then I have a parameter w, which is also in dimension d. And often this is called the weight vector, and actually eventually it will be weight matrices. So that's why weight and matrix, associate together. Weight vector is a rare cases. And then you also introduce another number b. This is called bias. And then you define your model like this. Say ReLU of W transpose X plus B. This is the inner product between two vectors, and you get the scalar out of it. And then you add another bias, which is still a scalar. So the output of this is a scalar. And so then basically we have like high dimensional inputs and one dimensional outputs. This is actually called a one layer network. So basically you apply this ReLU once. So and now let's try to kind of like stack multiple. So this is one neuron actually, because you apply one activation in some sense, it's one neuron. And then you can have multiple neurons. So I think one of the typical examples I used to give, maybe this is not exactly the best example these days. For example, let's say, suppose you think about the housing price, right? So it probably depends on a lot of intermediate features. Suppose housing price depends on, for example, maybe let me give you the full example just to slow down a little bit. Let's say, suppose you have this cases where x1 is the size, x2 is the number of bedroom, and x3 is, let's say, the zip code, and maybe x4 is, let's see, what's maybe the, I don't know what x4 is in my notes means, but anyway, so this is your raw inputs, right? So maybe you can think of like there are some intermediate things that actually matters more than this raw inputs. Let's say you have intermediate quantities like, for example, you say walkability, right? how easy to walk around the house, right? Maybe there's another one which is like the school quality. So these are, in some sense, variables that are not present in your original data, but they matters a lot to the price of the house, right? And each of this, maybe let's call this A1, this is A2. Each of this is actually a function of x1 up to x4, which can be computed as some nonlinear function. So you can imagine that A1 is probably some kind of like a nonlinear function of, maybe value of some of these linear combinations of this thing. And you can imagine maybe A2 is also some nonlinear function of this, of maybe let's say theta. I'm using notations in a pretty sloppy way just to give you an example. Finally we're going to define things more formally. And then you can say, oh, maybe my final y should be a linear combination of these guys. Maybe I have another parameter, maybe theta 9, A1 plus theta 10, A2, something like this. So then this way you kind of like stack two layers on top. You have two neurons and you stack another linear functions on top of it. So in some sense you are applying this recursively. So that's kind of like the fundamental idea on how do you kind of compose. So basically you apply these nonlinear functions, you apply a linear function, you apply some nonlinear functions, and then you get some outputs, and then you apply another linear version, and you can probably apply another nonlinear function here, and then you keep compose. So that's the rough idea. But let's try to make it a little bit more formal, so that it's probably more obvious. Let's see what's the right way for me to erase this stuff. I think we can probably start from the left. So one of the ways that people at least used to draw this kind of things, at least 10 years ago, was that they draw this kind of like inputs like this. So suppose you have x1 up to xd, and then you say I have some intermediate variables a1 up to ad, maybe am, and then each of the intermediate variables depend on all of this, and they have some dependencies here. So let's say am depends on all of the input variables, and you just draw these kind of edges, and then you can say I have another layer of intermediate variables, and they connect to each other. So these drawings are, once you know what they are talking about, the drawings are very useful, but when you don't really know what they are talking about, it's kind of like confusing. So what I really mean here is that, the way you do it is that you say first, let's do only one layer, maybe just to formulate. So we have x1 up to xd, right? So then let's have a1. The first intermediate variable is defined as maybe value of w, say 1 x1 plus b1, where w1 is a vector, even though I have an index 1, but it's the first vector, w1 transpose. And x is here. X is a d-dimensional vector, w1 is a vector. So the inner part together, you get a scalar, and you add a scalar b1 here. That's how you get a1, which is kind of like what I wrote there, like a1. So I use W just because I think people use W and B to distinguish the weight matrices and the biases. And then you have A2, which is a value of W2 transpose X plus B2, where W2 is RD and B2 is in R. And then you have a bunch of this. Let's say you have like up to AM. Let me see whether M is my notation here. It's very easy to mess up the notation in this kind of cases. Yes, AM is value of WM transpose X plus BM. And that's how you define A1 up to AM. And each of the AI depends on all of the Xi's in this particular way. And then you can say, I'm going to apply another, my output will just be a linear combination of all of these AIs. Let's say the output is some linear combination of the A's plus another B, plus another biases. So here is the thing. How do I write a linear combination of the AIs? I can write something like theta 1, A1, so on and so forth. But if I always kind of expand this, it's too complicated. So what I'm going to do is I'm going to write a vector, let's say W transpose A plus another B. But you realize that, when I write this, this W needs to be distinguished from other Ws. So, and that's why I think I'm going to use this 2 to say that this is the W on the second layer. In some sense, these are the Ws on the first. So there's another. So all of these AIs are combined to H theta X. And that's why people write this is the W on the second layer. And these are the Ws on the first layer. So I'm going to write another bracket WA1, something like this, to distinguish the first layer and the second layer. So, and this W2, superscript bracket 2 is a vector of the same dimension as A, not of the same dimension as X anymore, because you have to compile. You have to inner product with A. So this is in dimension Rm because I have M entries here. And B is always a scalar. So that's how you define a two-layer network. So you have a lot of image, and you can see this notation is kind of messy, right? So like, you probably shouldn't, when you have like too many superscript subscripts, at some point it's kind of like too messy. So that's why for most of the cases, some cases you have to live with these kind of notations. But in most cases you can simplify even further. You say, actually, if I write everything as matrices and vectors, I don't have to really think about each of these details. So basically, I just write A as a vector this is a vector in Rm. You can write as value of a matrix W times X plus B. And here, W and B are a little bit different. Okay, so W, I guess I need to write W1 and B1. So this is a matrix, W1. If you want to understand the correspondence between this notation and this notation, so W1 is this matrix of dimension M by D, and each row is W1 transpose up to WM1 transpose. Right, so you put all of these row vectors, because once you transpose, by the way, all the vectors are supposed to be column vectors if you don't do any transpose. If you really want to understand this, you should try to understand at least when, depending on the situations, right? But in many cases, it's good to keep in mind, whether this vectors is a row vector and column vector. So all of these are column vectors, and then you can transpose this, into row vectors. So this is a row vector, and you put all of them, stack them into a matrix. And then this B1 is just the vector of all the scalars. But in many cases, you actually don't have to necessarily remember this correspondence. You just remember this is fine, right? You have a vector, you multiply a matrix, you get a vector, and then you add a vector bias, and you take value entry-wise. Okay, that's probably important. So value applied to a vector, T, is the same as you applied entry-wise. So in many cases, you just say, one matrix multiplication, one layer is just a multiple matrix, add a bias vector, and apply value, and you get a vector out of it. So you don't have to necessarily understand all the details. Sometimes you do, but in most cases these days you don't have to. So, and if you count how many parameters are there, right? Like this is M by D. This is the dimension. So M by D, right? Because the input dimension is D, the output dimension is M, and you need a matrix that turns the D-dimensional input to M-dimensional outputs. That's why you need M times D parameters. And then this guy has M parameters. So the total parameter count is MD plus M. So D is the input dimension, M is the output dimension, and this is output dimension.
Is the B sort of one, as in the first layer there?
This is B1, yes. And this B1 is this B1. Yeah. So, any questions? And I think, eventually, actually, many of these details don't even matter if you don't care. So, for example, you can even just write this, For example, you can just say, oh, I even simplify notation here. You can say, I think you can say, let's just say this is a matrix multiplication. So let's say you have a matrix multiplication with W and B. So W is the weight matrices, which is this W, and B is the bias, and you apply Z, and this is just equals to WZ plus B, and then you can say I'm going to apply a sigma. Sorry, let's say sigma is I guess maybe I didn't. Probably I go a little too fast. I see. So maybe just before I talk about that, I think I already allude to it. So this red loop here can be also replaced to other nonlinear activations. So you can replace so the red loop with some other nonlinear activations, and all the other activations are functions that maps R to R. So it's always a scalar function, and but you can apply this to vectors by entry-wise applying entry-wise, and other activations could be like sigmoid. Sigmoid look like this. Let me just save some time to now define the equations. You can read the lecture notes to see the exact equations. There are also 10H, which looks like going through 0 and like this. So all of these activations are generally increasing functions, but not always the case. I think there's also leaky value. There's a bunch of different activations functions. For example, leaky value looks like. None of this is actually used that much. If you want to see what's used in the latest network, I think you have to check the lecture notes. I just added a few, which I don't have it on my notes. But there's also functions like this. Anyway, generally it's kind of like some almost increasing functions, and often on the left-hand side of the 0 is kind of close to 0, but not exactly right. So for example, the one that I just draw, this is called Jelu. Let me not write. I think the definition of it is, the Jelu's definition is this, just in case you care about the exact equation. So it's not exactly nonlinear, it just it dips a little bit. I think it doesn't go above 0. It's like this, strictly speaking. So it dips a little bit and then goes up. So exactly why you use any of this is kind of like a magic. Like I think people seem to find out that using some kind of somewhat smooth functions is actually useful. So ReLU is actually not necessarily great because it's not smooth enough. But other than that, I don't really know exactly. There's like sometimes it's just a stability thing, sometimes it's just a trial and error. So that's the activations, and then so now I'm trying to compact it. I'm trying to kind of have more and more abstract versions so that you don't have to deal with all these notations. So then once you have the activations, you can define this, right? So this is just the sigma of W, Z plus B. This is the abstract version of that. And then you can compose many times. You can say, I'm going to apply another one. So my model can be like, say, apply a matrix application on top of this sigma. And then, right. So WB, Z. And then apply another thing, right, so on and so forth. And each of this is one layer. And then if you apply another matrix application, sigma is another layer. And then if you do another one, it's another layer. The number of layers is defined as pretty much as the number of matrix application. Yeah. But here, one thing I'm a little bit scrappy about is that I didn't really tell you what's the parameters here in this matrix application. So technically, if you want to write this formula, you have to say, oh, this is WMB and this is what? Is it still using WMB or some other B? So oftentimes you use a different W and different B. The shape is similar, but the the variables are different variables. So then you have to introduce the bracket again. So let's say this is the bracket 1, B1, and then here the parameters are bracket W bracket 2, B2, so on and so forth. And then you index each of them to fully specify the network.
Is that matrix just a n+1 row matrix with the lots of bias vector transpose?
Which matrix, sorry?
Like the NN sub, like W.
So this matrix?
Yeah.
Yeah, so, okay. Yeah, so what these matrices are, so the only requirement is that you need to make sure that dimensionality is compatible, right? So, so your input, wait, did I write Z here? Oh, yeah. Okay. So let's say suppose your input Z is, say, dimension D, then you can only apply a matrix, with, so to make WZ make sense, you have to make sure W is of dimension something by D, right? And then something is what you can choose, almost freely. Of course, not all the options are the same eventually in terms of the results, but for the compatibility issue perspective, you can choose them arbitrarily. And let's say suppose the first layer you choose, let's say suppose you choose, let's say you choose matrix application, say, W1, B1, Z plus Z. And suppose this W1 is M1 by D. So that means that you map this D-dimensional vector to M1 dimensional vector. So let's say, so this output is going to be M1 dimensional vector. And then next time, okay, and if you apply a sigma, it's still M1 dimensional vector. And next time you apply the matrix application, you have to make sure that the input dimension of that matrix to be compatible with M1. So basically, if you do another one, say W2, B2, then it's required that W2 needs to be something times M1 dimension. And something, the output dimension is still what you can choose freely, but the input dimension is not. And the next, and you have to do this, again and again. So once you have multiple dimensions, then, so basically maybe the easy way to think about it is that you have a matrix, right, times, say, Z plus B, right? So this dimension is what I call the input dimension, because this dimension got multiplied with the dimension of Z. And this dimension is the output dimension. But the output dimension becomes the input dimension for the next round. So that's why you need to make sure all the dimensionalities to be compatible. That makes sense? Yeah. And in many cases, I think, the original input dimension is something you cannot change, right? So that's fixed, that's based on your data. And then afterwards, you don't change dimensions that often. You typically use the same dimensions for quite a while. Maybe you change it once or twice, something like that. Okay. And, if you, just in case you read some of the old papers, which, and I think even these days, still the architecture papers sometimes draw like this, like they just draw, people go more and more abstract, right? They say, I have an input X, and then apply a matrix modification, and then apply another, maybe sigma, and apply another matrix modification, so on and so forth. That's how people actually draw these networks, without specifying all details. And you can even merge these two together to call it MLP. So sometimes you will just draw this. You have X, and if MLP is called multi-layer perception. Often it encapsulates one or two layers of this, a few of these components. When people say MLP, I think sometimes it's one matrix modification, one sigma. Sometimes it's two matrix modification, so on and so forth.
I have a question. So usually, do the weight vectors become smaller in size, or do they usually become bigger in size? Is there a common strategy there, or?
I think in most cases you get smaller dimensions. The intermediate dimensions become smaller, and that's often because the input dimension is often very big. For example, for language, it's kind of like your initial, the vocab is kind of like the token. I guess I'm jumping ahead a little bit, but your initial dimension could be 250K or something like that, and then you shrink it to probably 2K, and then keep using 2K. Yeah, something like that. And for vision, I think the same thing, because initially you have a RGB encoded kind of image. you have three RGB, three numbers, and each is like 256 by 256, or maybe depending on the resolution, and you have to shrink it a little bit. Yeah. Okay, what else? I think one thing is called ResNet. I think that's still useful, so probably I should tell you about it. So, let me erase something here. So, but eventually, like you can define many components like this. Most of these components are matrix multiplications, activations, and I'm going to tell you a few other components that are still largely being used, in different cases. And some of the very modern cases used in like more modern components like attention used in language. I'm going to talk about those in the large language model lectures. So these are some. So one of the components called residual network, or just residual connections. If you think about the component, so the residual connection is like this. So instead of keep using this kind of things, the residual connection is kind of like, let's call residual Z, is this interesting thing where you have two applications of this alternating between matrix multiplication and activations, and then you add your input again back to it. So one thing that is actually, at least by definition, it means that you don't change the dimension here, right? Because to make this compatible, your input dimension, output dimension are exactly the same. And of course, these two matrix multiplications are not using the same weight matrices. I'm not just write exactly what they are, but they are not using the same matrices. And this is called a residual block. And this was introduced like in 2015 in this very famous residual network paper. I think the kind of the rationale was that if, let's say, suppose, by the way, this Z doesn't have to be our original raw input. This could be one intermediate layer, and then you apply this Z, you apply this residual block, and then you can actually apply many residual blocks. So eventually this is called residual block, and eventually the residual net looks like, with some approximation, it's kind of like you apply a lot of residual net many times. And at the beginning, you need to kind of do something maybe to change the dimension, because you cannot work with the original dimension. So you first change the dimension to some dimension of the intermediate dimensions, and then you apply many residual network. And maybe you have to apply one more at the end to change the dimension again. But largely speaking, it's application of many residual blocks. And that's called residual network. And the original motivation was that, why you apply this? That's because suppose you believe that at some point you are already getting close to your labels, right? So suppose at some point, Z is already approximately equal to Y, let's say. Y is your target, and Z is your intermediate variables in some intermediate, layers. Then, you probably should model the differences explicitly, because you're already kind of close. You just probably should use the networks to model only the differences. So basically, you should probably just model Z minus Y as some residual, or maybe Y minus Z, sorry. Say Y minus Z as some residual of Z. And if you believe in that, sorry, not the residual of Z. If Y minus Z to be some kind of like network, say something like this. Plus, right, like this. Right, so if this is your belief, then if you move Z to the other side, then you have Y is equals to sigma M Z plus Z. And you can see that this is kind of like almost the same as here. The only difference is that they found out actually you probably shouldn't use a one layer to model the difference. You should use two layers to model the difference. So they say, oh, let's say you do two of this. And then the same thing you just have like this. So this is just a story. It's not like there's any formal proof there. And actually people have tried to, 10 years ago people have tried, maybe 7 years ago people have tried to see how many blocks here you should do. Can do 2 layers, 3 layers, L layers, and eventually I think 2 or 3 layers are the best. Also for reasons we don't fundamentally understand necessarily. So that's residual network. I thought, yeah.
Like the hypothesis though, I thought like that the term on the right, that's our hypothesis. I'm unable to understand why that's case.
So suppose this is the modeling assumption. You model only the differences, then so this implies this, and they are the same, right? So like which one is the hypothesis depends on what you believe in. So but somehow if you somehow believe that it's more beneficial to model directly the residual, then you do this, right? And then you change and you rearrange to get this. That's the only thing I'm saying. Nothing profound. And there are other kind of like explanations for why this works. For example, some of the theorists, they try to analyze the optimization perspective of different modeling, right? So basically, if you don't add z here versus you add z, in some cases you can argue that adding z will make the optimization easier, make your optimization more well conditioned, including some of my papers. I think there's some degree of truth there as well. It's just it's very hard to fundamentally, it's like you have many explanations for for it. It's very hard to know exactly which one is the right explanation. Yeah. Maybe let's see. I have 7 minutes. Any question?
A little bit more intuition for why the differences can be modeled by like this.
There's no, I got the question. What's the intuition? But like, maybe let's see. So the intuition could be that, maybe this is already small, then maybe I should directly model that, right? As opposed to model the original label. So it's a simpler task. The original label, predicting original label is very hard, but if you predict the difference, probably it's easier. So that's why you model easier tasks with the two-layer networks, and that's pretty much it is. Like there's no, nothing more formal than that. Yeah. Let's see. I have 7 minutes. I think, let's see. Should I have time to talk about 2 things? Okay. So maybe let me quickly talk about, layer norm. And I can see whether I have time to talk about the convolutional network. So layer norm is also something that people still use, in large language models. So of course in slightly different form these days. So the original layer norm is the following. So basically it's a component, right? So like it's a block, so you have some input that's called z. And this component is trying to normalize z in some way. And the way to normalize it is that you say you first turn z into some normalized version of z, which is z minus mu1 over sigma 1, comma z minus mu m sigma m. Let's say z is m-dimensional. z1. No, my bad. I should read the note. I should follow the notes more closely. I think this is of the same. Yeah. Maybe I should even use. Yeah. So let's say. Okay, I don't remember why I use hat, but let's use hat. So this is how you normalize, where mu hat is the empirical mean, which is the average of all the z's. And sigma hat is the empirical, sigma hat square is the empirical average of the standard deviation. So this will empirically normalize it to norm 1, right? So you can see it's pretty standard. And then it's not done yet. And then you turn this into, sometimes people found out, actually mean 0 and norm 1 is not that great for whatever reason. So they say, let's be flexible. Let's also add, a flexible tunable parameters, beta and gamma. So the next step is turn this into beta plus gamma z1 minus mu hat, sigma hat. Where beta is a tunable parameter. Beta is a variable that you can tune, and gamma is a variable you can tune. So basically this make a mean beta and a standard deviation gamma. So that's the original layer norm. And then later people realized actually you probably don't have to do this. You just, so this is the layer norm. And now I think there's something called RM-SAM norm, which is even simpler. You don't subtract the mean anymore. You just divide by sigma. So you just say you do z is turned into z1 minus sigma 1 sigma hat. Say z minus sigma hat, and the sigma hat is also different. Sigma hat is only the average. Is only kind of like you are only averaging over like you don't subtract here. So you just try to make the so sigma hat is something like 1 over m zi squared. And then you still do the beta thing, right? Then you turn this into beta plus z1 over sigma hat. You know, why this is kind of like more better or not, you know, I think it's mostly empirical. So basically here you don't really want to make it, let me think about this. Wait, sorry, I think you still need gamma. Sorry. Did I keep gamma or keep the beta? I keep the gamma, sorry, my bad. You do this. So, and gamma is tunable parameter. So basically this is saying like, I don't have to care about the shifting mean. I don't really make it mean 0, but I still care about normalizing it in some way. But I still leave some degree of flexibility gamma, which it's not really normalizing. I still allow it to be normalized to something that I will decide later in my training. Right. So this is kind of like the magic here. It's not like you try to force it to normalize to 1, standard deviation 1. You actually say, I first normalize to 1 and then I leave a gamma, parameter there so that in the training I can normalize to anything. I think, let me see. Yeah, I only have 1 minute. So one benefit of all of this is that you make it kind of like a, scaling invariant in term for both the parameters and the data. So what does that mean is that if you multiply, so maybe let's say you call this whole thing called, let's say z, let's just say z, right? So like, let's say, suppose this whole operation is called a layer norm. So you apply z and you get a layer norm of z. And you can find out that there's a scaling invariant, which means that if you apply a scalar, let's say you multiply a scalar, say alpha to z, and you get ln alpha z, but ln alpha z is actually equals to ln z. So basically, no matter how you multiply the input, you don't really change it. And so that's why no matter how you multiply your matrices or you multiply your input data, you never change the output. Unless you change some of the parameters like beta and gamma, which is, in your test time, you're not supposed to change them. So basically this makes the model more scaling invariant. And in some cases, it helps, stabilize the model. For example, at least intuitively, with some degree of approximation, there are at least in the past when people tune all of these models, it happens that sometimes you apply these layers many times, and then the output becomes bigger and bigger, and it becomes like really big. It's like 10 to the 20 or something like that, and then then everything just blows up. So when you normalize every time, then you never got into this issue, and also it makes the initialization a little bit more kind of like easier, so that you don't have to before, like if you don't do something right, then suddenly everything just blows up, and now like the scaling doesn't really matter that much. But there's also subtlety here, because when you have, okay, this might be a too advanced comment. Like one side effect of this is that when the forward pass is scaling invariant, but actually the gradient is not scaling invariant still. So some of these issues got pushed into the optimization. So, which is, a much more complex matter. Anyway, so I guess, let's see. So I think I'm done. The only thing I didn't cover is the convolutional network. I think it's in the lecture notes. So, if I spend 1 minute on it, I think it just means that, instead of multiplying a full matrix, you actually multiply a topless matrix. I'm not sure you heard of this word. So basically it's a matrix with some structures where so when instead of having this matrix, convolutional network just basically means you have a matrix that's kind of look like this. The non-zeros are only like this. And it's actually the same set of non-zeros. So like you shift this vector here and you put it here and you put it here and you put it here. It's actually called like a filter in some sense. Like, so this matrix, all the other parts of the matrix is 0 and only this, what I drew here is kind of non-zero, and also they share the parameters. So basically this vector is the same as this vector. So you apply kind of like a shifting invariant kind of like filter to the data. And it's called convolution. Oh, of course, the real thing is a little bit more complicated because when you have 2D and so on and so forth, it becomes complicated. But in the lecture notes, we have that. But the convolutional network is not that used that much, except for very hardcore vision cases. Like even for vision cases, people use language models like transformers a lot. So that's why probably it's fine to skip them. Okay, sounds good.